Assalamualaikum and hello everyone. We are from group number 5, consists of Akil, Neo, Lok and me, Ayu, gonna present about flash separation design for acetone chloroform mixture. This is the list of contents that we're gonna cover in this video. First, the introduction of VLE. Vapor-liquid equilibrium describes the distribution of a chemical species between the vapor phase and a liquid phase. In a binary mixture, this principle allows us to separate the components as the more volatile vaporize, while the last one remain in the liquid state. Next, flash separation is a single-stage separation process used to separate a liquid stream with multiple content into separate components. The separation is triggered by a sudden pressure drop across a valve, causing the feed to instantly vaporize. Inside the vessel, gravity split the phase where vapor rise to the top outlet while liquid settle at the bottom. This project aims to design a flash separator to separate an acetone chloroform mixture into vapor and liquid phase. The study includes reviewing suitable operating conditions such as temperature, pressure, and feed composition, and performing flash calculation to determine the mole and composition of each phase produced.
Hi, I'm Lok Bin, and now I'll explain about the details regarding the process flow diagram (PFD), property of substance, assumptions, temperature estimation, and the saturated pressure calculation. Let's start with the process flow diagram. The basic assumption is one of equimolar liquid mixture containing acetone and chloroform are fed into the fresh separator. Both substances will operate at a temperature of 25 degrees Celsius and 101.325 kilopascal for the inlet stream. At the outlet stream, we have both vapor stream and liquid stream operate at the temperature of 58.7 degrees Celsius and the pressure of 101.325 kilopascal. This is the property of the both substance. Assumption. For the ideal solution, the binary mixture behave ideally, meaning Raoult's law will apply without an activity coefficient. Equilibrium stage. The fresh separator achieves vapor-liquid equilibrium (VLE) instantly with no mass transfer resistance. Third, constant pressure. The system operates at a fixed pressure. Negligible heat loss. The separator is perfectly insulated, so no heat is lost to the surroundings. No chemical reaction. The mixture components are inert and do not react under operating conditions. 6. Single stage separation. Only one equilibrium stage is considered. No multiple flashes or rectifications. 7. Constant molar overflow. The molar flow rate of the vapor and liquid phase are steady and balanced according to the mass conservations. Temperature estimations. So for this calculation, we take the average of the boiling points for both substances, which is 56.25 plus 61.15 degrees Celsius divided by 2, and we get 58.7 degrees Celsius for the outlet streams. Endpoints equations. The tables here shows the details coefficients for the endpoints calculation later. Calculation of saturated pressure. So this shows the endpoint equations and the endpoints calculations for both acetone and chloroform. For the acetone, we get the saturated pressure of 110.2674 kilopascal, while for the chloroform, we get the saturated pressure of 93.6473 kilopascal. Now I'll pass to my teammates to continue with the presentations.
Dr. I'm Yong Junwei. Before conducting any flash calculation, we must first confirm that the two-phase mixture actually exists at our chosen condition. To do this, we need to calculate the system bubble point and also dew point pressure using the Raoult law. On the left, we calculate the bubble point pressure, which is the pressure where the first bubble of the vapor formed. Using our feed composition of 0.5 for both acetone and also the chloroform, this gives us 101.9574 kilopascal. On the right, we calculate the dew point pressure representing the pressure where the first drop of the liquid condenses. This evaluates to 101.28 kilopascal. The operating pressure 101.325 kilopascal is fall directly between the PDP and also the PBP. Since the system is in a two-phase region, the flash separation can occur. Moving on into the flash calculation, we assume an ideal solution to determine our equilibrium constant K value. The K value acts as the distribution coefficient calculated by dividing a component vapor pressure by the total system pressure. This yields a K value of 1.0883 for the acetone and 0.9242 for the chloroform. Next, to find the mole of the vapor, we plug this K value and our initial feed fraction into the Rashford-Rice equation shown on the left. This will give us a total vapor stream of 0.9338 mole, while we subtract this from our 1 mole feed basis will yield a final liquid product stream, which is 0.0662 mole. Lastly, for the calculation of the vapor and liquid phase mole fraction, we use the Rashford-Rice component equation for the vapor phase to find an acetone fraction 0.5027 and chloroform at 0.4973. Then applying Rod's law for the liquid phase, our fraction are 0.4619 for the acetone and 0.5381 for the chloroform.
To summarize, this is our final process flow diagram of our flash separator. We have 1 mole of liquid mixture of equimolar acetone and chloroform in liquid phase, entering at 25 degrees Celsius and leaving at 1 atm. In the vapor stream, we have 0.9338 mole of the fraction of acetone is 0.5027 and 0.4973 of chloroform, leaving at 58.7 degrees Celsius at 1 atm. And in the liquid stream, we have 0.0662 mole of acetone, we have 0.4619 mole, and 0.5381 mole of chloroform, leaving at 58.7 degrees Celsius and 1 atm. To verify our answer, we pulled up a TXY diagram from ChemiCalc of the same binary mixture and at the same temperature. And as you can see, the liquid fraction of acetone is 0.46, which is very similar to our flash calculations of 0.4619.
In conclusion, the single-stage flash distillation was successfully designed and proved for the separation of an equimolar acetone chloroform mixture. Operating at a temperature of 58.7 degrees Celsius and pressure of 101 kPa, it was shown thermodynamically that the process operates within the two-phase region. The final model achieved a dominant phase distribution where 93.4% of the feed was flashed into vapor and only little amount remained as liquid. That's all from us. Thank you.